All right, so we want to start by looking initially at increasing and decreasing, and then see what these critical points are. And as we find the critical points, then see, okay, what use do these things have? All right. So first of all, what does it mean for a function to be increasing or decreasing, and then how does that relate to the derivative? Okay. So if I'm looking at this parabola on the left, as I go from left to right, where is it decreasing?
Well, in the middle? Oh, I thought you were on the same picture.
The parabola.
Where is it decreasing?
Where is it decreasing?
The origin?
Until the origin.
It's not.
Okay, up until you get to the origin, right? Okay, so up until you get to the origin, it is decreasing. Okay? And then it starts to increase from here up to infinity. Okay? So there we're increasing. Now how about this cubic equation over here? Where is it decreasing?
From the beginning, from the middle of the first thing to the origin, to there to the other thing. I don't know how to play it. Like,
well, look at it.
-1 to 2.
Yeah, from x equals
-1
over to
so
2. You can't see? Do you have any glasses?
Yeah, I have glasses. It's really bad.
Alright, well. Okay, so there we're decreasing. Okay? There we're decreasing. And then we're increasing from negative infinity up to where negative 1 is. And after we pass 2, it's increasing here as well. Okay? Now, the question here is, how is this relating to the derivative? Okay? Now, to answer this question, I want us to look at some tangent lines. Alright? If I have tangent lines on the decreasing parts, okay, and over here I'll do tangent lines on the decreasing parts as well. Here's tangent lines. Okay, what do you notice about all of those tangent lines?
They're going down.
They're going down. They have a negative slope, okay? Now, think with me here. When it's decreasing, the tangents have a negative slope. What does that mean about the derivative?
It has to be negative.
It has to be negative.
Oh, yay.
Yes, it's exactly right. F prime is negative. Okay? F prime is negative. So, and that's something that we're going to use quite a bit. When we find, if we can tell when the derivative is negative, we will know then when the function is going to be decreasing. And vice versa. If we see a function and we see that it's decreasing, we know that the derivative will be negative there. Okay? Now, let's look at, let's do purple. Okay? The increasing parts. So there's a tangent, there's a tangent, there's a tangent. Okay? Over here. Here's a tangent, a tangent, a tangent, a tangent. Over on this part where it's increasing, those are all tangents. Okay? What's true about all of those tangents?
Positive slope.
The tangents have positive slope. Okay? That means our first derivative is positive. Okay? Now, what about those points where it changes? What do you notice about where those points are on the graph, first of all?
The horizontal.
They're what?
The horizontal.
Okay, you remember when I told you when you were finding these the other day that they were going to be important? Okay. The horizontal tangents occur between where it is increasing and where it's decreasing. Okay? Right there, the slope of the tangent equals 0 right here. Okay? Over here, there's 2 points where the slope of the tangent equals 0. There's one, and there's one. This is why I had you guys solving those problems where the slope of the tangent was, where did we get the horizontal tangents? Okay? Slope of the tangent equals 0. Slope of the tangent equals 0. Where does that occur? On these graphs? They're at max and min points, okay? So, max and min points will always occur when your derivative, or when these are what we call critical points. So we'll hit that term a little more, okay? So max and min points are at, or not, I should say, are where the derivative equals 0. Okay? There's one additional possibility, but we'll look at that in a sec. Okay? So, that's what we're talking about here with increasing and decreasing. This is the concept, believe it or not, that's going to help us solve numerous kinds of problems throughout the next few units. Alright? Now, there's a couple of terms. These are not terms that are used a whole lot in IB, but I wanted to know them just because they're good to know in calculus, period. Okay, but if we have monotone increasing or decreasing, that just means that the function does not change at all. It doesn't change from increasing to decreasing, so there's no max or min points. Okay, so here are two examples. Here's an exponential growth and an exponential decay function. The logarithmic function is another one. The radical function is another one. X cubed. X cubed, except for 1 point, would be increasing everywhere. Alright, so that's something that you can see here. And if you know a function is going to be monotone increasing or decreasing, and you're asked to find max or min points, there are none.
And so there's also no horizontal tangent.
Exactly, there's no horizontal tangent.
So if we just like see a problem that says, find the horizontal tangent, it's one of these, then we can tell.
Yeah, you could say that's an exponential function, it's always increasing or decreasing depending, so therefore there are none. Huh?
Monotone is exponential, same thing.
No.
No,
Monotone is like one. Like monotone voice is only one pitch all the time. Monotone just means one tone. So here, we're not changing direction at all, increasing or decreasing. No, exponentials are an example of a monotone increasing or decreasing function.
It just means that it's only increasing, it's never gonna go decreasing.
So one of the tools that we use here is a sign diagram, okay? This is essential that you guys understand how to make these, alright? The sign diagram. So we have this function x cubed minus 3x plus 4. I want to step you through how to make the sign diagram and then what that tells us about our functions, okay? So imagine that you don't see the picture of the function there for a moment. We're just going to start with the graph. If we wanted to know what that graph looked like, these are the steps that we would take. Okay, first of all, you're going to find f prime of x and set it equal to 0. Okay? Alright, so we're finding f prime of x, and secondly, we're going to solve f prime of x equals 0. Alright, so f prime of x is 3x squared minus 3. So I set that equal to 0, 3x squared minus 3 equals 0, and I solve it, okay? So we divide everything by 3, we get an x squared minus 1. So we know x has to be plus or minus 1, okay? Now, those are the places where we have horizontal tangents. Those are what we call critical values, okay? Critical values, okay? Now, we can find the points on the graph by plugging them back into the original equation, all right? I have the point 1, and if I plug a 1 in, I get 1 minus 3 plus 4. So negative 2 plus 4 is 2. So the point 1, 2, and then I have negative 1, and that's going to be negative 1 plus 3 is 2 plus 4 is 6. Okay? Those are what we call critical points. Okay? So, pay attention to those two terms. A critical value is just a value of x. A critical point is actually a point, x and y coordinates. Alright? Now, what we just found were these 2 points here, negative 1, 6, and 1, 2. Alright? But let's look at actually making a sign diagram. So when you're doing a sign diagram, you just make a number line like you see up here, and you're going to put the two critical values, any critical values that you have, you put on here. And notice that just divided the entire number line into 3 sections. Okay? The other things that you would put on the sign diagram that we'll run into later are anywhere where the derivative is undefined. So like if you use the quotient rule, you might have things where the derivative is undefined. Okay, so you'd put that on there too. Now, this is where, now that we've solved it, we put the critical points or critical values on a number line. Okay, and then test each interval to see whether the derivative is positive or negative. Okay, test each interval to see if f prime is positive or negative. Okay? So what are we doing there? Well, let's look at our sign diagram. I pick any number that's to the left of negative 1. So negative 2. All right? If I plug in negative 2, I get 3 times a negative 2 squared minus 3. Well, that's 3 times 4, which is 12, minus 3 is 9. Now, the thing is, I don't really care what that number is. All I care about is what the sign is. All right? I don't care that it's 9. What I care about is the fact that it is positive 9. Okay? Now, what that tells me is that if the derivative is positive at negative 2, it's going to be positive everywhere from negative infinity all the way up until I get to negative 1. So what do I know about the function if the derivative is positive? It's increasing. So I like to draw myself a little arrow like that to show the function is increasing. Okay? So now we pick a number between -1 and 1.
0.
0, yes. Make your life easy. Pick easy numbers. So 3 times 0 squared minus 3 is -3. So we just figured out that the derivative is negative for every number between -1 and 1. Okay? So what do I know about the function? It's decreasing. So I like to draw a little arrow like this. So I know it's decreasing. Now, think with me here. If I'm increasing as I approach -1 from the left, and then I start to decrease, what do we have at -1? A max. Okay? When you see a change from increasing to decreasing, we have what we call a local maximum point. Okay? This is where we have a local or relative is another term for that. Local or relative max. Okay? Notice that's because we have a change from increasing to decreasing there. Okay? So now let's test our last interval. If I plug in a 2, f prime of 2, I have 3 times 2 squared minus 3. Well, that's going to give me 9 again. So my derivative is positive for everything past 1, which means my function is increasing. So now look at where x is 1. If I was decreasing as I come towards it from the left, and then I start to increase, what must we have at 1? Huh? Are you guys with me? Okay, we have a minimum. Alright, so we have a local or relative min at x equals 1. Okay? Now, the reason why that's helpful is because now, even if this weren't drawn for me already, I know that, hey, to the left, I have to be increasing as I approach this -1, and that's going to be a max because then I start decreasing until I get to 1, and then it starts to increase again. So you can see here, even if this weren't drawn for me already, just what I just found would let me get a pretty decent sketch of what this looks like. Okay? Now you might remember in pre-calc honors, what you guys did with quadratics, you were able to find max and min points because it was always right between the two zeros. You know, you find the zeros, you average those x values, and that's where your axis of symmetry was and your vertex was. Okay? But when you had the cubics, even if you found all 3 of your zeros, the rest was just kind of guesswork. We used the end behavior, and that gave us an idea of what things were. We might find like the y-intercept to help us out, but that was the best we could do. Now we can actually find what those max and min points were, or are, okay? Another thing here, notice, we often will write the intervals where the function is increasing or decreasing. So you notice I used interval notation, and notice I used parentheses, not brackets, because at -1 and 1, we're not increasing or decreasing. It's 0. And that's why these critical points also have another name. Okay? And by the way, this is what makes some of the vocabulary challenging with these, is that there's more than one name for pretty much everything. Okay? They're called critical points. Another name for them is stationary points. And not the E-R-Y like a letter you're writing. A-R-Y, like standing still. Stationary. Stationary points. Stationary is just a fancy word for not moving, remember? Okay? So, these are points where our object, if we were looking at its rate of change is 0. It's not moving, it's stationary. Okay? Alright. Alright, so just to recap here what we did in the example, we found the derivative, and then we found where the derivative equaled 0. We factor that out, we solve it, and we get x is plus or minus 1. Okay, so we put that on a number line, and that divides the whole number line into 3 regions. We test a value in each of those regions, and whether it's positive or negative tells us whether the function is increasing or decreasing. Okay, and remember this term, the term critical value or stationary points. Okay, critical points or stationary points. And why do we call them stationary? Yeah, because that's the moment where the object, if our function is modeling motion, for example, that's going to be the one moment where it is not moving at all. It's not increasing, it's not decreasing, it's standing still for that one moment. So that's why we call them stationary points. Now, critical values are not necessarily going to always be max or min points. Okay? They're not always going to give us a max or a min point. Let's take, for example, the cubic function. All right? The cubic parent function. We know that this goes through the origin, through 1, 1, through 2, 8, 3, 27, and so on. -1, -1, -2, -8, and so on. So our function looks something like this. Now, you can see here, just looking at the graph, we can obviously tell that there are no max or min points there. However, we do have this point right in the middle where it kind of looks like we're going to have a max or min, because it levels off. But then we changed our mind and we decided to keep increasing. Okay? And that's what we call a plateau point. Okay? A plateau geographically is an area of land that is just a raised flat area of land. Okay? It's a plateau. Well, that's the same idea here on the function. It's a part where the function was increasing, it levels off, but instead of going back down, it just continues to increase. Or it can go the other way as well. We could decrease, level off, and then keep decreasing. But let's look at how we find those. If I were to take the derivative of y equals x cubed, I get dy dx is 3x squared. So where does that equal 0? Where does 3x squared equal 0?
0.
At 0. Okay, so the critical value is 0. If I were making a sign diagram out of this, there's my number line. I put 0, and then I need to plug in something to the left of 0 into my derivative. So if I did 3 times a -1 squared, that's a positive 3. Okay? So, and I could see this from the graph in this case, but notice since that's positive, my function is increasing. Okay? And then, if I were to plug in something to the right of 0, like a positive 1, 3 times 1 squared is also positive 3. Okay?
Won't it always be positive because it's always squared?
Well, yeah, and that's the thing with this. Other than at 0, this will always be positive, and that's actually what we just showed. And that's how we know that the function will be increasing everywhere except for that one point at 0. Okay? But notice here what happened if we do not have a change in direction, no change in sign, no change in the sign of f prime, okay? If there's no change in the sign of f prime, that means we have a plateau. Plateau. Thank you, France. Okay? So, when you have the derivative equal to 0 or undefined, we'll run into some of those as well. Critical values, remember we said, happen when the derivative is 0 or undefined. Then, if the sign changes, you're going to have a max or min. If the sign does not change, you have a plateau. So let's take a quick look at this one here, okay? We have this function. Find the intervals where f of x is increasing or decreasing if f of x is x cubed plus 5x squared minus 4x minus 20. Now, you sketched graphs like this back in pre-calc honors, but you weren't able to actually find max or min points, okay? So here we're going to be able to do a little bit more, all right? In pre-calc honors, the best we could do is get the y-intercept and the zeros, and then use end behavior, all right? So actually, before we even do anything with the calculus, let's look at that, that part of it. Notice I can factor this original function by grouping, okay? I factor by grouping, and I get this all down to x plus 5 times x squared minus 4. That means I have zeros of this function when x is negative 5 and plus or minus 2. Okay, so I can actually put this on the graph, plus or minus 2, and also negative 5. I also see that this has a y-intercept. That's easy to find. Where's my y-intercept? Negative 20. So there's negative 10. It's going to be down here. Okay? Now, is that a min? I don't know. Okay? But I also can tell, because my leading coefficient is positive, I know that the function is going to go up as we go to the right. Okay? And because the degree, the highest degree is odd, I know the left side is going to do the opposite. So I know that this is going to go down to the left. Okay? Now, if I use my derivatives to find the intervals where it's increasing or decreasing and identify max or min or plateau points, I can fill in all the missing stuff. And we can actually get a really good sketch of what this function would look like. Okay? So, the best we could have done back before calculus was say, okay, well, maybe it goes up to here, it goes down somewhere around there, and then it goes up, and there we go. Now we don't have to guess so much. So let's do this part. The first thing, if we're trying to find critical points, is to do what? Find the derivative. So, f prime of x equals
3x squared plus 10x minus 4.
There we go. 3x squared plus 10x minus 4. Now, you can try to factor that. It doesn't.
Yeah.
So how do you
So
solve?
quadratic?
So we got to use the quadratic formula, okay? So we're trying to find critical values, so we set this equal to 0. So I'm going to use the quadratic formula. X is negative 10 plus or minus square root b squared 100 minus 4 times 3 times negative 4. So it's going to be plus 4 times 3 is 12 times 4 is 48.
Are we gonna get this formula?
All over 2a. Well, actually, this formula, the quadratic formula, is actually in your formula booklet. We really shouldn't need it at this point, but just in case you blank on it, it's there. Okay? So, now we have negative 10 plus or minus the square root of 148. Since we're graphing, we'll just use decimals here. Okay? Square root of 148 is going to be about 12.1, because 144 would be 12. And 12.1 would give us 3 significant figures, so that's good enough for SL.
Nice.
Then we divide by 6. Okay? So when we do negative 10 plus the radical 148, we get point, what did we say, 06 or point
361.
361, or negative 3.69. That's what we get when we subtract the radical 148. Okay, and this actually would be rounded to 12.2. Okay, so that being said, we can now draw our sign diagram. So I'm going to put a number line here. I put negative 3.69 on the number line. I put a positive 0.361 on the number line, and I pick numbers to plug into my derivative. Okay? If I picked, say, a negative 4, negative 4 squared is 16, so that's 48, minus 40 is 8, 8 minus 4 is positive. Okay? So I know that this will be positive, which means my function is increasing until I get to that negative 3.69. Okay? Now, with polynomials, we know that polynomials follow nice little patterns as long as we don't have double roots or triple roots or whatever. So this is going to go negative and then positive. Okay? But we can plug numbers in just to double check. If I plug a 0 into the derivative, I get negative 4. 1 is in this interval, so if I plug in a 1, I get 3, plus 10 is 13, minus 4 is positive, so that's there as well. Okay? So now I know the intervals where f of x is increasing or decreasing. Please don't forget to answer the question. Just showing a sign diagram is not giving the intervals. Okay? We are increasing on the intervals from negative infinity up to a negative 3.69. And from 0.361 up to positive infinity. Okay? So those are the two intervals where our function is increasing. We are decreasing between those two critical values, 3.69 to 0.361. Okay?
Okay.
Yeah, I get it.
So those are x points.
What?
On the actual graph, those would be the x values, where there's the...
Those are the x values, yes. So now that we have our critical values, notice I can see on the sign diagram that because I was increasing before negative 3.69 and decreasing after, I know at negative 3.69 I'm going to have a maximum point. Okay? There's going to be a max point there. And at 0.361 I'm going to have a minimum. Okay? Now we had already seen enough from our graph that we figured that was going to happen. Right? But even if this were some other kind of function that we weren't able to sketch this much without calculus, we would be able to tell those things now. So, to find the actual points, what do we need to do?
Plug them into the
Plug them into the
initial equation.
original equation, that's right, okay? So now we need to do f of a negative 3.69 and f of a 0.361 and find what the y coordinates are. Okay, so once I plug those into the calculator, I now know that my min point is that point negative, or sorry, 0.361 negative 20.7. Alright, so if I look here, my y-axis went down through that negative 20. Okay, the actual min point is going to be just next to it on the positive side at 0.361 negative 20.7. Okay, so now I know that this graph looks like this. Okay, and just do your best to sketch. Okay, I also know that the max is up at 12.6 at negative 3.69, so it's going to be somewhere right around here. Okay, so that's what the rest of this looks like. Okay, so the max is the point negative 3.69, 12.6. Okay? Now, I made this kind of level off a little bit here. It shouldn't actually. It should just go straight through that point. Okay? But again, that's something that as you sketch, just do your best to make it look right. Okay? Any questions? Okay. Now, our goal here is not just to be able to, sketch these functions by hand when we could just throw them into our graphing calculator. The fact of the matter is, every one of these features that we find, depending on what our model is modeling, our equation is modeling, it's going to tell us something else about the situation. Okay? If, this is a model modeling the movement of an object, okay, and our x-axis is like a center point, or let's say the object is moving up and down in the air, okay, and that 0 is where it would be if it was like sea level or whatever, then we can go ahead and figure out exactly how high it goes, exactly how low it goes, and we can also take the derivative to tell us what speed or what velocity it's traveling at any given moment. Okay? That's partly why we model these things. Okay?